So today we're going to look at optimization problems. Basically, given a situation, we're going to go ahead and try to find the max or min for that situation. Now, for the most part, these are the kind of the general steps you want to follow. Find what you're trying to maximize or minimize, whether it's volume or area or length or something like that. And a lot of these problems are going to require two equations with two variables, not necessarily all of them. And then whatever you're trying to maximize or minimize, you want to go ahead and get that only with one variable in it. Then you can go ahead and find your critical points by doing your derivative and looking and see where your derivative is 0 or undefined. And then you can do your extrema. And then a lot of these you're going to have to look at what your domain would be, because your domain will be limited based on the real life situation. And then make sure you actually answer the question that was being asked. So for this particular problem, we have a farmer that has 200 yards of fencing, and he has 3 sides that he's going to be using the fence on, because one side's along a long existing wall. So we're going to have fence here, fence here, fence here. We want to know what are the dimensions of the maximum area. Well, if we go x here and y here, we would know x times y would be our area. And we're trying to maximize our area. So we have our area here that we're trying to maximize. However, what we have here doesn't work for us to take our derivative because we have two variables. So we want to find another equation that relates our variables. Well, we've done nothing with this 200 yards. Well, wouldn't 200 have to be the total distance of our fence, which would be all this, and then this side here, which would be an x. So our total distance of that red fence would be 200 yards, and that's made up of an x here and an x here, so 2x, and that y. So what we want to do is try to only have one variable here. So we need to solve this for x or y. I think it's going to be easier to solve it for y because there's nothing in front, and we would get this. So now all I want to do is to take that y and plug it in right here. And I would get this. Now we can go ahead and distribute through and do our derivative. Set your derivative equal to 0 and solve it. And in this case, we would get 50. But we should also look at our domain. Well, our domain, we have to look at what x is. What's the shortest x can be? Well, the shortest x could be would be 0. Well, what would be the biggest x could be? Well, the biggest that x could be, as we look up here, biggest x could be would cause your y value to be small. So think about what's the biggest or what's the smallest y could be. Well, the smallest y could be would be 0. Well, if y was 0, if y is 0, that means x would also be 100 then. If you go y being 0 and go 200 is equal to 2x, you get 100. So that's the max and min of our domain. So your critical points that we're going to check are 50, because that's the when your derivative is 0, and the two endpoints. And there's two ways to do this. You could do it like we did in section 1, checking your two endpoints and checking your critical points and plugging them into your original function. And so you plug in 0. Well, if you're 0 times anything would be 0, or 100. So those would be your mins, which means you would just have a fence that would be 200 yards long right next to your wall, which you wouldn't have any area. Or if x is 0, plug that into your original function right here, or the purple one, wouldn't make a difference, and we would get 5,000 yards. So we would know that this would be our maximum. Now we got to answer the question. It says, what are the dimensions? It doesn't want to know maximum area. It wants to know the dimensions that give you the maximum area. Well, that means x would be 50 yards. Well, if x is 50 yards, can't we plug it in here to find y? We'd have 200 minus 2 times 50, so we get y to be 100 yards. Now, there's a second way we could have done this. We could have done a labeled number line segment. Normally, we say it's a labeled number line, but in the context of this problem, it would have to be a line segment because this is 0, this is 100. Your only critical point was 50. Then you try a number between 0 and 50, like 25, plugging it into your derivative. 200 minus 4 times 25 would be 200 minus 100, which is positive. So we'd be going up. Try a number in between, like 75. Plug 75 in here. 200 minus 4 times 75, which would be negative. So we'd be going down. So we'd have a max right here at 50. That's another way you can go ahead and show that you have a maximum there, besides looking at your closed interval from section 1. So, next problem. Read through this and then start the video again. So, we're looking for our maximum area of our beam. Basically, we want this rectangle in our circle to be the biggest possible. Now, for simplicity, you may want to go ahead and think of the center of your circle as being the origin, like that being 0, 0. So then going from here to the edge of your rectangle would be like going over x. Going from here straight up would be like y, with your radius being 1. Now, could you have your radius go straight to the right all the way out to your circle being 1? Yes. But I think it might be helpful here. By the way, if we're looking for the area of our rectangle, if this is x, this would also be x. So our total width would be 2x. Looking at our height, if this is y, this would also be y, so our total height of the rectangle would be 2y. So our area would be the 2x times the 2y. Or we could write it as just 4xy. And we're trying to maximize your area. Well, we can't do that here because for your derivative, because we have two variables, we only want one. So what's a second equation we could use over here to relate x and y? Well, it's a right triangle. So we could go x squared plus y squared equals 1 squared. Now, we could solve this either for x or for y and then plug it in over here. If I solve it for y, I could then go ahead and I get this. Now I'm going to take that and plug it in for my y right here. If I plug it in over there, I'm going to get this. And you might be wondering, why did I get rid of the plus or the minus? Well, in the context of my problem here, isn't y going up? I had y going up, so that means we can only have a positive length. It would not make sense to have a negative length, so that's why I got rid of the plus or the minus. Well, now that I have what I'm trying to maximize my area into one variable over there, I can do my derivative. Well, notice you have variables times variables, and have to do the product rule. Derivative of the first times the second plus the first derivative of the second, put the exponent in front, decrease the exponent by 1. Then remember chain rule times the derivative of the inside, which would be a negative 2x. I would probably do a little bit of simplifying here because you have multiple things multiplied together. So I would probably go ahead and multiply this, this, and this together. Well, I would get this here. Now, could you leave it with negative exponents and fractional exponents? Yes. Could you then have pulled out a fractional exponent of the negative 1/2 power? Yes, you could. There'd be nothing wrong with it. But remember, we're trying to find our critical points. So all we have to do is set it equal to 0. I really have a fraction minus a fraction equal to 0. So I could really just go ahead and take that second fraction and add it to the other side, and then I'd have a fraction equaling a fraction, and then I could solve it from there. Now, if I wanted, I could multiply both sides by my denominator. So then I'd have this root times itself again, so it'd just be 4 times the 1 minus x squared. On the right side, I would just get this because those would cancel, and then you could solve it from there. And in this case, we get x squared to be equal to 1/2. Take the square root of the top, square root of the bottom. I get 1 over root 2, get the root out of the bottom. So I get root 2 over 2 as my critical point. What are the other critical points? Well, that would be the endpoints of my domain. Well, the smallest x could be would be 0. The biggest x could be, well, x could go all the way over to the edge of the circle, from the center to the edge of the circle. Remember, our radius was 1, so the biggest x could be would be 1. So we could go ahead and check each one of these. Plugging in 0 to your original function, plugging in 1 to your original function, plugging in root 2 over 2 to your original function. So if you plug in 0 to your original function, now we're plugging it into the original up here, then you would end up getting 0. If you plug in 1 to that original, you get 0 inside of your root, you'd also get 0. Plug in root 2 over 2, you end up getting 2. So x being root 2 over 2 gives us our maximum. If x is root 2 over 2, plugging it in right here would allow us to find y. If x is root 2 over 2 and squared, 1 minus that inside your square root, you also get root 2 over 2. So in other words, x and y are both the same. And once again, we are looking for what shape would give us the cross-sectional area. So I'm saying what shape, to me, I'm thinking that means length and width. If x is root 2 over 2, remember the whole length is, you got to double that. So if x is root 2 over 2 times 2, you get root 2 for the whole width. And remember, y goes up and down from here to here, but the whole height is 2 of those y's, so you'd have to double that y, which is root 2 over 2. Times 2 would be just a root 2. So we get our dimensions to be root 2 feet by root 2 feet for a total area of 2 square feet. Now, keep in mind, instead of doing the endpoints in your critical point, you could have done, once again, a numbered line segment. And we'd have to remember to label this A prime. Our one endpoint was 0, our other endpoint was 1 because that comes from our domain up here. Put our only critical point on here. Try number in between each 0 region, plugging it into your derivative because that's what we have listed in front. And then to see if it's positive or negative. And we were looking for a maximum, and you plug it in over here, you get a positive, you'd be going up. Plug it in over here, you'd be going down. So that's another way to know that you have a max right there at root 2 over 2. So one last problem. So pause the video and read. So we have a wire from here to here. So we're wondering about total length of the wire. So that would be y here plus z over here. Now, we only want to have one variable. We don't want to have two variables. But as you look over here, isn't this a right triangle? So can't we go x squared plus 12 squared is equal to y squared? So I should be able to go ahead and solve this for y, so I could plug it in up here. So y is this here. Once again, y has to be a positive length, so I don't have to worry about the plus or minus. So instead of writing y, I'm going to write what I have for y right here and plug it in. We can also do the same thing over here. Isn't this over here a right triangle? So I can go my one side squared plus my other side squared equals my hypotenuse squared. So the horizontal side squared plus the vertical side squared equals my hypotenuse squared. I can solve that for z. Once again, z has to be positive. And so instead of writing z here, I can write what z is here. So plugging in z, I would get this. Now that I have my wire length, w, with only one variable, I can do my derivative. Now you could do your derivative as it is, or you could go ahead and FOIL out that 30 minus x all squared and then add your 28 squared. And that's what I did here. Now we can do our derivative. Exponent in front, decrease it by 1, chain rule! Well, if you simplify all that for the first part, you would get this. I didn't show all my work. Here, doing your derivative here, you'd put your exponent of 1/2 in front, decrease it by 1, and then multiply by the derivative of the inside, because that's the chain rule. If you simplify that big ugly fraction, you would get this. So in this case, when you're trying to do your critical points, you'd have to set it equal to 0. Well, there's a couple ways you could do this. Since you have a fraction equaling a fraction, you could just take one of these to the other side, subtract it over. Subtract it over, so I'm going to have a negative there. And then we could really just square both sides, or we could cross multiply and then end up squaring. It would not make a difference. So if you go ahead and basically cross multiply, because it's a fraction equaling a fraction, we get this. And you might be wondering, where's the 30 minus x come from? If you take this negative and distribute it into the parentheses, you get a negative x and a plus 30, so that's why you get this. So now we could go ahead and square both sides. So we could square this, and we could square this. But keep in mind, we have two things multiplied, two things multiplied. When you're squaring two things multiplied, you can really apply the square to each part. So you can really square this, square this, square this, and square this. Well, we get an x squared. Your squaring on the root cancels that out. Over here, 30 minus x all squared, your squaring on your root cancels that out. So we can distribute through your x squared. I would take 30 minus x, FOIL that out, and then you'd have to take that times this here, so that would be big ugly, but here's the answer. Now, notice, you have an x to the fourth on each side. You have a minus 60x cubed on both sides. So you just have some quadratic stuff here equal to a quadratic here. So really, it's just a quadratic equation. So set it equal to 0. And then you could try to factor or quadratic formula. First of all, I'd pull out my greatest common factor. It does factor quite nicely, but if you wanted to use quadratic formula, you'd be welcome to. It wouldn't make a difference. And you would get two answers of 9 and negative 22.5. Well, in the context of your problem, it doesn't make sense to have negative 22.5. You can only have a positive length. So we know we're only going to be dealing with 9. Oh, by the way, the smallest x could be would be 0. The biggest x could be, well, the biggest x could be would be to be able to go from here all the way over to here, which is 30 feet away. So the biggest x could be would be 30. So your domain is 0 to 30. So you have your two endpoints, 0, 30, and you have your critical point of 9. Plug them into your original function. And then you can see which one gives you the minimum length, which is right here. Now, once again, instead of using your closed interval, you could have done a numbered line segment, just like we talked about before, where this would be your W prime, your critical point of 0, your critical point of 30 for your endpoints, your critical point of 9. Try number in each region into your derivative, because that's what it's labeled as, and you would see that you would get this, and so you get a minimum. That's another way you could go ahead and show it.